Hello, I'm Boris Galitsky, and I will tell you about discourse-based tool series for logical validation of large language models. The plan is like this. We start with validating LLM, explain why LLMs need to be validated, and describe our proposed system valid LLP for LLM. LLP is a label logic program. It's extension of reasoning specifically for validating the capability to reason in a broad variety of domain using different reasoning methods. Then we explain how discourse is used to represent domain knowledge for validation, relying on discourse. Then we formalize and explain how labeled logic program work, and we complete with evaluation. So obviously LLMs achieved impressive results, but integrating them into domains that demand structured, verifiable, context-sensitive reasoning is still difficult. LLMs rely on associative rather than strategic reasoning, and it limits ability to perform multi-step decision-making. Also, there's a problem how in our charts LLM can revise conclusion based on new information. So limitation again, associative, not strategic reasoning, and the struggle with systematic multi-step context-sensitive things, poor revision on a new individuals, hallucinations and logical inconsistencies, and this is our main target. So validation tries to identify and repair hallucinations. If multiple reasoning, formal reasoning result is different from LLM result, then it is suspicious. And with different configurations, it can reject LLM results or update it. The other limitation is black box nature. There's no traceable arguments. So there's limited trust in high stakes domain like healthcare, economy, legal. LLMs can be coupled with external reasoning, and verification layer can enforce logical consistency and does explicit explanation. So what is promising and what has been done in a number of work is pairing LLM with symbolic reasoning agents, especially in Prolog. But it's mostly classical straight Prolog. Then LLM answers what produces LLM are considered candidate, and reasoning model can, with the help of LLM, also building ontologies, facts and clauses. And this candidate answer can be confirmed or rejected. And the contradictions or supported claims will be flagged. This goes under umbrella of neurosymbolic solution. So LLM is neural, verification is symbolic, and architecture is hybrid. So LLM proposes and logic disposes. Candidate answers are checked against formal rules. And again, this formal rules representation from text is also done by LLM. Can be one example of formalization, the feasible logic program, and that also makes a bridge to discourse. Implicit reasoning can be represented as a verifiable logical argument, and the benefits are contradictions, corrected conclusions, so we have explainability, and also once we have corrected subset of answers, if it is fed back to LLM, it can improve it via fine-tuning. So valid LLP for LLM is a hybrid neurosymbolic framework. Unlike for Berlin first approach, the system doesn't require reclassification of logical formalism. So we doesn't need to determine if it's temporal, probabilistic, spatial, argumentation. It covers all possible reasoning domains. So multiple reasoning dimensions are encoded within structured labels. And how discourse helps? Discourse-aware methods transform textual explanation and domain knowledge into label facts and rules. So discourse information it's one source to attach labels to facts and rules. For example, nucleus versus satellite. Nucleus more important and satellite less important and only valuable in the context of nucleus. So a ratio between different rhetorical relations gives us weight. So different rules acquire strength, different strength value based on occurrence in discourse representation of text. So traditional way, what we have is for first LLM is asked to not to solve the problem, but classify which logical formalism is required. Then it finds necessary solver, determines for temporal, for spatial, for model, for probabilistic, and this specialized solver is targeted. So advantage of this approach is conceptual clarity. We are very clear what kind of logic, but the limitations are depends on correct classification, which can be wrong, and the coverage is limited because sometimes solvers need to be compiled. Sometimes it is about space and about time. So the solution here, labeled logic program, eliminates need for formalism classification. Instead of selecting a single logic up front, system uses universal labeled reasoning substrate. LLM translate problem directly into LLP representation consisting of labeled facts and labeled rules. These are for temporal, model, argumentative, probabilistic, and so forth. And then a verification engine evaluates the same LLP for different tasks plus domain-specific ontology also encoded in this LLP and different what we call logic profiles. And this is what I described on the left is traditional approach, and on the right is our approach. Basically, it repeats and shows what I just said. Let's talk about discourse. So advantages of LLP approaches is robustness and extensibility. Most reasoning dimension already embedded in the label algebra, so we don't have to reinvent it for each problem. Multiple reasoning styles can be combined in any possible way, and as a result, LLP reduces brittleness of conversion from natural language to logical ontology formalisms, avoid missing method failures in classical logic program, and provides unified explanation. So back to discourse. Each rhetorical relation has a nucleus and a satellite. Nucleus important, satellite less important. Strict rules, defeasible rules. So we have for nucleus strict rules, for satellite defeasible. And defeasible logic program is a partial case with the defeasible clauses and clauses with always hold. And then we have on the left list of different rhetorical relations, and this is a strength, confidence, weight, nucleus versus satellites. Quickly run formally define it's instead of just fact A in logic program, we have T semicolon A. A is object level statement, and T is a structured label that stores meta information such as time, when it was inferred, from which source, which modality, what kind of arguments are supported, and different ways to express uncertainty. So both facts and rules are annotated with labels. For rule, we can have associated with labels specify evidential status like obtained from electronic health record, measured from patent, complaint, and so forth. the four components of LLP labeled facts, algebra, operating with priority relation, operating on aggregation, label discipline, how labels are introduced, transformed, and combined during inference. And inference rules look as this. If multiple derivation exist, labels are aggregated. To support multiple logical formally simultaneously structured labels are time, space, model, provenance, argumentation, and so forth. And this yields a single LLP that can be projected into different logic. A logic profile P is a configuration, specify which label component, constraints define compatibility, how propagation functions are working, how it's aggregated, and whether defeat flattening is applied. And now we can switch to Prolog code. This Prolog program interpreter for labeled logic program. So you can see its facts, rules, and derivations enumerated of labels. We have profiles for temporal model argumentation and with flags which sub-profiles are used and how profiles are set. And then we have meta-predicate proof using profiles and sub-proofs. And they look like applying rules, proof body, combined rule. This is what I explained in formal terms implementation in Prolog. So we have verification, what I explained, claim extraction, label assignment in the same format I just described, capturing time, source, like different facts can have different time, associate different sources, more reliable, less reliable, argumentated in different way. Then we do multi-profile verification, injection before the, like in this domain, injection occurred before the complication. Argumentation profile, argumentation considers exception. Maybe there is additional treatment. They may defeat the rule. And probabilistic profile propagates uncertainty and checks if confidence falls below, and we basically cannot complete this inference. And each profile yields a labeled verdict. So we have there for each claim what is supported, what is defeated, and what is uncertain. And then after that, we perform meta aggregation. So for comparison, we enumerate the components we evaluate against the label logic programming, Horn close logic, explicit negation, probabilistic logic programming, abductive, and argumentation. Speaking about implementation, we have set of tools, discourse parser, a logic program runner, rule attenuation, diagnosis making verifier, argumentation framework solver. So each of these rules gets input either in natural language or in logic program implementation and can do specific verification. In this case, domain specific. So it's this example, probabilistic logic programming, argumentation, and so forth. Let us get back to demonstration. Now, evaluation data set, we use different hallucination data set, truthful hallucination, medical hallucination, PubMed QA, and the natural language inference. We convert them into question answering pairs and inject controlled inconsistencies. We artificially inject hallucinations so we can then detect them and flag as a golden set for known hallucination. And define hallucinations are defined. Claim defeat probability is above 0.9. Also, we perform aggregation of evidence from multiple reasoning components as we described in label logic program, and we predict hallucination accuracy. This is just logic programming, arguments, and label logic programming, which we see there for these data sets and also our own data sets. Arguments sometimes improve, sometimes perform not as good, but uh, label logic program outperforms in most cases, other than our own dataset, which is more complicated. So result confirms that combining labeled symbolic reasoning with discourse weighting yield the most robust hallucination detection performance. However, there are open challenges for clinical narrative data. And I think that's less about reasoning, it's more about still harder for this data set to automatically build ontologies, because that's just a part of the pipeline. And if there's a limitation in building ontologies, even if reasoning is robust and expressive enough, you still cannot confirm, validate LLM. We also do human evaluation with respect to accuracy, delta in confidence, human logic agreement, calibration error, and interpretability. And with that, we also uh, measure just LLM, a logic program, argumentation, abduction, and full LLP for LLM. And reasoning traces help the users to understand system better, and discourse helps. We are done and we're ready to do conclusions. LLM usually sound right, but not necessarily reason right. We added logic where LLM proposes and LLP verifies, and no need to pick a necessary logic. One framework does it all. Discourse tells which rules and how important matter, strong versus weak evidence, and as a result, we have fewer hallucination, better trust, and it is explainable AI.